All right, well, we're going to talk about the different kinds of reactions. We're going to start with single replacement since we've already talked about double replacement. So, with single replacement, one atom is going to replace or displace the similar type of ion in a different compound. Okay, so an atom is going to replace the ion of a different atom, um, usually from solution. So the first type, a metal can replace hydrogen from either water or acid. And when I say check the activity series to see if this reaction occur, well, in honors, we had those reactivity series that we could use. In AP, we cannot. But the thing about AP is that they will not give you a reaction that won't occur. So you don't have to check. You just have to recognize what type of reaction it is. So if, for instance, we had aluminum in water, we know that the aluminum can replace the hydrogen because hydrogen is like a metal as far as it's the positively charged ion when it's an ion. So we can kind of always relate hydrogen to metals. So if you're given a metal in water, you know that the metal is going to be replacing the hydrogen in water and combining with the hydroxide. So, like this one here, uh, always think of water as HOH in reactions. So the aluminum can kick out one hydrogen and combine with the OH, and then you have to balance your charges. So aluminum is always +3, OH is -1. So you need three OHs to combine with your aluminum. The hydrogen that gets kicked out must pick up a partner to become H2 because of Hofbrinkel. There's no such thing as H by itself. So anytime a metal is replacing hydrogen from water or acid, it's kicking out one hydrogen, but you never ever just have one atom reacting with one molecule. So the hydrogens that get kicked out combine together and you get H2. Okay, and you have to balance charges and then balance your overall equation. All right, so same thing if you have sodium in water. Think of water as HOH. The sodium kicks out the hydrogen and combines with the OH, so you get NaOH plus H2. That H that gets kicked out has to pick up a partner to be H2. You do not get NaO or Na2O. Think of water as HOH. Okay, do not think that the two hydrogens get kicked out to form H2 and Na2O. The OH is what combines with the metal. So you're always getting a base, you're getting the hydroxide with the metal, and then you balance the equation overall. So that's a metal in water. In acid, a metal will replace hydrogen also. So if we put nickel in hydrochloric acid, the nickel kicks out the hydrogen and steals the chlorine. Nickel is most commonly +2 as an ion. So when it picks up the chlorine, it'll need two of them because chlorine's -1. The hydrogen that gets kicked out, again, has to be H2, so it's picking up a partner. Okay, so metals in acid kick out the hydrogen and combine with whatever the anion is of the acid. The product's always H2 plus the metal with the anion. In water, it kicks out one hydrogen, steals the OH. You always get a hydroxide and H2. So in both cases, you're getting H2 formed, and then the metal combines with whatever the other ion is. In single replacement reactions, you do have to write ionic equations when there's ions present. So if it is a solid, it is not an ion. But if it is a strong acid or a soluble ionic compound, it has to be split up into ions. In this first equation here, aluminum solid with water as a gas, or if it's water as a liquid, either so water doesn't split up in an equation into ions. And then this aluminum hydroxide that's formed is a solid, so there's no ions splitting up, and then it's gas. So there is no ionic equation for that first one because we have all solids and gases. But in this one, hydrochloric acid is really H plus and Cl minus, and there's two of them in the balance. And then this nickel chloride that's formed is aqueous because it's soluble in, there's water present in the acid. Okay, if it's aqueous acid, then there's water. So that compound nickel chloride is soluble. And so it splits up into ions. Then the hydrogen gas that's formed is not ionic. It doesn't form ions. So then the complete ionic would be here in the red. Nickel plus that goes to those two ions plus H2. So what's going to cancel is the chloride ions. So the chloride ions cancel, and then here's your net. Nickel solid plus 2H plus goes to nickel plus 2 plus H2. Very common type of reaction where we put metal in a strong acid. The anion of the acid will be canceled out if the product is soluble. All right, so what would these make? Again, think of water as HOH. This one I actually already did up there. So we get NaOH and H2. And then we have to balance it because I've got more hydrogen on this side. So putting a 2 there and a 2 there gives me 4 hydrogens, 2 oxygens, 2 sodiums. So then it's balanced. Again, solid, gas. So if it's solid and a gas, then we would have this be a solid and a gas. If it's gaseous water, there's no liquid water around. You're going to get the metal turning into solid, not, it won't be split into ions. But if this were liquid water, then the sodium hydroxide would be split up into ions. There would be nothing canceling though, because the liquid water doesn't split up into ions. The sodium solid is not the same thing as Na plus. So there would not be anything canceled. It would just be, if this was liquid water, the NaOH would separate into 2Na plus 2OH minus. So it would have an ionic equation if this was liquid water, but as gases, not. Okay, so then this one, same, zinc solid with hydrogen chloride gas. Still, the zinc is going to replace the hydrogen and make H2, and that will be gas. And the zinc is going to combine with the chlorine. Zinc is plus 2, so we would need 2 chlorides. And then to balance it, I would need a 2 here. But again, if there's no water present, this is zinc solid plus hydrogen chloride gas, then this would have to still be a solid. Okay, so it's only when water's present that things split up into ions, like this one up here. This was aqueous acid, or if it were liquid water. Another kind of single replacement is a metal replacing another metal. Again, you don't have to check the activity series in AP because they don't ever give you a reaction that doesn't happen. So if you're given zinc plus copper sulfate, you know that the metal can replace the metal. So the zinc is kicking out the copper and stealing the sulfate. The charges would be the same in this case because this was copper 2 sulfate, and zinc always is plus 2 as a metal ion. So we just get zinc sulfate and copper. But when you see aqueous, you have to break apart the ions. So zinc solid doesn't change, but the copper sulfate is copper plus 2 plus SO4 minus 2. And over here, aqueous. So it's really zinc plus 2 and sulfate minus 2. And then we have copper solid. It didn't say, but it would be a solid. So what cancels is the sulfate ions. What's left is solid zinc plus copper plus 2 goes to zinc plus 2 plus solid copper. The zinc and the zinc plus 2 don't cancel each other out. A solid metal with no charge is not the same thing as a metal ion. They do not cancel. So a metal replacing a metal, the aqueous tells us we have to split those compounds up into ions, and then the sulfate canceled out. The third kind of single replacement is a halogen replacing a halogen. So this one, we just look at the periodic table, and any halogen higher on the chart can replace a lower halogen, not vice versa. So we look, chlorine is higher, so it's more reactive than bromine. So yes, chlorine can kick out bromine. Remember Hofbrinkel, it's Cl2, not Cl by itself. So when it kicks out the bromine that gets kicked out, just like hydrogen, has to pick up another bromine to make Br2. And then we balance the charge between K plus and Br minus, and we just need one of each. So it's with the chlorine. So the chlorine that gets kicked out, we just need one of each. So it's KBr. So then to balance it, I would need a 2 here and a 2 here. Okay. Again, what do I see? Aqueous. What does that mean? It's breaking up into ions. So this is really 2K plus 2 Br minus. The chlorine didn't change. And notice here that we were just on the other ones, it was always the first element that was getting replaced because the metal ion came first, the hydrogen came first. But this is the halogen replacing a halogen. Don't replace a hydrogen or a metal with a halogen. That can't happen. Like has to replace like. A halogen can replace another halogen, not a metal, not a hydrogen. So the chlorine replaced the bromine. So then Br2 is a pure liquid. It's not split up into ions. And then this is aqueous. So 2K plus 2Cl minus is the what that splits up into. So then the only thing that cancels are the 2K pluses. So what's left, I'm going to write in blue, is Cl2 plus 2Br minus goes to Br2 plus 2Cl minus. That's the net ionic equation. In single replacement and double replacement that we did yesterday, anytime you see aqueous, you're going to be breaking it up into ions. If it says gas, liquid, or solid, do not make ions out of it. This next one would be bromine trying to replace fluorine. No, that's not going to happen. When we look at the periodic table, fluorine's the most reactive halogen. None of the other halogens are going to be able to replace it. So that is no reaction. Okay, so 3 different kinds of single replacement reactions. You need to know and be on the lookout for all 3 of those. So that's single replacement. So yesterday we did double replacement. This is single replacement. And then just review, there's combination or synthesis where 2 elements are making a compound, or there's other kinds where you could have 2 nonmetals making a compound. So you could have a metal with a nonmetal making a compound. You can have two nonmetals making a compound, but the key is in combination or synthesis, you will only have a single product. So they might be individual elements combining, or it could be a compound combining with the element that's already in it. Rarely are you going to have a compound just add in a completely different element, or rarely are two different compounds just going to combine. So these are the most common types of combination or synthesis. Two individual elements combining to make a single product, or a compound that has some element in it and then you add more of that element, and then sometimes you can get a different compound. Okay, but the key is you always have one product. Also notice these are all gases or liquids or solids. There's no ions, so there is no ionic equation. Even if the directions say write net ionic equations, there's no ions. This is the equation. This is the only equation there is when you're combining two gases, or a solid with a gas, or a liquid with a gas, or whatever. Okay, no aqueous, no ions. Right? Decomposition, just the opposite of combination. You're breaking apart one reactant into other things. It will be either breaking apart and becoming elements, or it could be becoming simpler compound and an element like this one. So this one, KClO3, when heated, will break down into KCl and O2. O2 is super common. The gases that you know of, CO2, O2, H2O, N2, those things, if they're common, that means that they're stable and they're often formed. Okay, so when you're looking at something, you think, oh, what could come out of that? Oh, oxygen could come out of that. Types of decomposition are thermal, which means you're heating it. Electrical, electrolysis, you're running electricity through it to break it apart. That's the way to break apart water. You run electricity through it and you can break it into hydrogen gas and oxygen gas. Simply heating water does not do that. Okay, another one, electricity, taking a salt, heating it so it's melted, molten, and then you run electricity through it and you can separate it out into the elements. Again, do you notice there's no water as far as liquid water, aqueous in these things. So a pure liquid water does not split into ions. And then liquids, pure liquids, gases, no ions. So again, in decomposition, you're not going to have an ionic equation. Right? So the last one, combustion, we talked about that. When you're burning something, the products are going to be usually gases or liquids. Again, there's no water here. You're burning it. No water, no aqueous, no ions. So you're not going to have ionic equations. Most common combustion is burning a hydrocarbon. You get CO2 and water. But anytime you're burning something, almost always, not always, but almost always, oxygen is one of the reactants. And then you get a product that is a combination with the oxygen. Okay, so burning magnesium is a combustion as well as a synthesis. You're synthesizing MgO. Okay, most common, burning a hydrocarbon. All gases, no ionic equation. Okay, so that is a review of the other types of reactions.